Let us start this lecture with a thought process from Albert Einstein, who says that without deep reflection, one knows from daily life that one exists for other people. This is a very important message that we should keep in mind while we are harnessing knowledge, and this knowledge basically will be meant for the people. Let us recall that what we had learned in the last few lectures. We basically started the discussion on vapor power cycle, right, and based on which steam power plant is being built, and then we also looked at the ideal Rankine cycle. Therefore, we also explored how to enhance the thermal efficiency by using the reheat method, right. We also superheated the steam, and then there was a limitation of the temperature of the boiler and the turbine material. So, therefore, in order to overcome that problem of limitation having the higher temperature at the inlet of the turbine and also the boiler, so we thought that we can do that reheat it, right. But is there any other way of enhancing the thermal efficiency? If you recall that there is a components of the heat addition, that is from the pump till it's what you call reaches the saturated temperature, right, 2 to 3 kind of things. There the heat addition is very less. Now, if you can operate on that, enhance that one, then we can enhance the average temperature at which the heat is being being put into the cycle, right, from the boiler. So, one way of doing that, we can preheat the feed water. What do you mean by this feed water? Basically, the water from the condenser, it will be getting back to the boiler. Am I right? Yes or no? So, we will have to preheat that what you call the heat, preheat the water from the condenser, what we call feed water, and then we will have to put into the boiler, so that it will be having a higher average temperature, right. Then we can enhance the thermal efficiency. Now, is it we will give externally, or some of the heat which is can be utilized for heating the feed water. So, what we will do, if we will give externally, then what will happen, we cannot really enhance the thermal efficiency, because work output will be similar in nature or same rather. So, therefore, we cannot. That means, if we can use some of the heat which is getting rejected in the condenser, then do that. Then we call it basically regeneration. In this case, what we do, we basically extract the steam from the turbine after getting expanded in the high pressure portion of the turbine or high pressure turbine. Then we will mix with that. Let us see how we can achieve this concept of regeneration. And so, if you look at this, basically the cycle is now modified. There is a boiler where heat being added, and then of course, this is usual to the any Rankine cycle, but then the steam will be expanded in the turbine, and some of the steam which will be extracted from here, maybe some portion of the turbine where we can call it as a high pressure turbine, low pressure turbine, depending on the pressure, because if pressure is very low, you cannot really put into that, because you need to have high pressure. So, the steam is being extracted. This is extracted steam from the turbine, and then it will be having a what you call open feed water heater. This is the heater, and of course, rest of the steam which will be expanded in the turbine further, and then of course, it will go pass through the condenser where it will be rejecting the heat, and then you will have to also pump it to the high pressure, and then it mixed together, right. And if it is mixed together, that is why we call it as a open feed water heater, right. And then it has to be also again use this pump to augment its pressure, so that it will reach the boiler, because boiler will be at high pressure, like, so that, and then it will be, and this completes your cycle, because we are taking some amount of heat and heating this what you call incoming fluid from the condenser, right, what we call feed water. That is why you call it as a regenerative cycle. So, this component what you call this modified cycle is known as regenerative cycle. And let us look at the processes little further, like further in the sense some of the things might be repeated, but however, just to embed that thing in mind, that I can say this is basically, if you look at something 4 to 5 and 6, right, this point is 6 basically, right, heat, here it is being heat added. You can say this is Q in, or I mean like you can say also this is Q in, right. I am saying Q1, Q in, okay. Now, it is being expanded in the high pressure turbine, right, and then sorry, it is expanded, and then it is extracted, steam being extracted, basically extracted steam, right. And then it is further expanded, the steam, rest of the steam, suppose you take few kg per second of the steam, here let us say 10 kg are there, you are taking 2 kg per second of the fluid from the steam, and 8 kg per second is being expanded further, it is going to the condenser where it will be rejected out, right, and then it will come back to the this saturated liquid point, and then it will be your pump, right, 1 to 2 is your pump, right. You can say pump 1, and this is basically pump 1, and this is your pump 2, right. And this is again like it will be mixed with this feed water heaters, and then again it will be pumped, that is from 3 to 4, this is your pump 2, right, and after that it will go back and this. So, this is the cycle what we call a regenerative cycle. But if you look at the open feed water heater, right, is being used, and so also the closed feed water heater, right. What is the difference? Is there any differences between this, if I say open feed water heater and closed feed water heater? In the open, the extracted steam, which will be high temperature, right, and it will be mixed with the cold fluid which will be coming from the condenser, right, I mean mixing together, and then it will be, the temperature will be raised, that is the open feed water. But there is another way of doing that, what is that? That is basically I can have an heat exchanger. For example, I can have a fluid here, let us say this is my heat exchanger, this fluid is coming from let us say what you call 2 to 3, and there is another fluid is coming from here, let us say, right, this is the cold fluid which is heated, and this is coming from the 8, right. I can say okay, again this is what you call I can say maybe 3 dash, right. Okay. So, this is the heat exchanger. What I call this is as a closed feed water heater. Are you getting? Because this heat, because this is the hot fluid, right. This will be, if you look at H8 will be much higher than the S2, enthalpy you can say, heat you can say, whatever you call, right. And therefore, there will be some heat will be coming to this fluid to here, right. We have seen already heat exchanger. So, in this case the fluid is not coming direct contact with the hot fluid is not coming directly contact with the cold fluid, but in this case it is all mixed together, right. For this what you need to have what you call another pump, but the advantage with the open feed water heater is that the effectiveness with which heat exchange will be taking place will be 100%, very high, right. And also it will be a very easy and simple system. You do not have to really have a very good material for the heat exchange, and then complicated of scaling problems, whenever heat will be there will be scaling problems and other things, and the pressure drop will be there, of course, right. But in this case the disadvantage with the open feed water heater is that you will have to use another pump, but whereas because the pump has to be raised, this liquid which will coming from the condenser will be at low pressure, right. This is the low pressure, right, okay, low pressure. Now, this has to go to this is high pressure. So, therefore, you need a pump, right, and then that also enhances the cost. So, if you look at in real systems, the generally combination of both open feed water heater and closed feed water being used, right. But if you look at, both are having certain advantages, both are having certain disadvantages, depending on to optimize that people use both, in the actual steam power plant. So, we will be taking this what you call open feed water systems and then trying to analyze that, and so what let us recall that what is being done here is basically heat energy that could be lost in the condenser is being utilized in heating the feed water. That means, we are basically regenerating it, we are rather you can say recovering it, the things. So, sometimes people call recuperative kind of things also. The such cycle is called regenerative Rankine cycle, and let us do the analysis. Analysis will be similar in nature, only the difference is that we will have to make a mass balance and the heat balance in a feed water heater. That is the only difference, rest of the things are same, and we will be assuming steady flow process, change in kinetic energy and across any component, and change in potential energy across any component will be 0. Like change in kinetic energy will be 0, change in potential energy will be 0, and then wherever work is there, it will be work will be given. Otherwise, in the expansion process we will be assuming to be isentropically expanded. So, also in the compression process, all assumptions whatever we have done for the other cycles like your reheat cycles and the simple superheated Rankine cycle will hold good. So, what we will do? We will basically look at a feed water heater. Let us say this is my feed water heater, feed water heater, right. I can take this as a control volume, and the fluid is basically, let us say it is coming with the this is your stream 2 and this is your stream 8, and it is going out with the stream 3, And what is that? This is basically mass is coming m dot 2 here and m dot 8 here. So, also S 2 and H 8, right, and similarly here mass 3 and S 3 enthalpy, right. So, what we will do, we can do a basically mass balance, that is mass flow rate coming from the what you call from the condenser, right, after the pump of course, plus the mass flow rate extracted from here from the turbine is equal to the total mass flow rate which will be feeding into the boiler, right. That makes sense. So, similarly, we can apply the first law of thermodynamics for energy balance to the feed water heater, that is m dot 2 into S 2 plus m dot 8 H 8 is equal to m dot 3 H 3. This is a simple what you call energy balance. And what we will do, we will have to look at it. I mean, instead of what you call these things, right, we can try to eliminate certain things, so that we can find out basically like a relationship, how much we are extracting. For example, like what I am saying, that here that you just take this m 2 here in place of m 2, right. From this expression I can put basically m 2 is equal to m dot 3 minus m dot 8, and this expression I can put it here, right. I mean, I can put it here, and then I will get m dot 3 S 3 is equal to m dot 8 H 8 plus m dot 3 minus m dot 8. I mean, like difference, that difference mass flow rate into S 2, right. So, if I divide this thing by what you call m dot 3 here, right, what I will get? I will just divide by this m 3, m dot 3 here, m dot 3 here and m dot 3 here, this will cancel it out, this will cancel it out. So, I will get S 3 is equal to m dot 8 by m dot 3, right. And if you look at what is this thing, that means the m dot 3 is the total what you call amount of water or the fluid which is passing through, that is the m dot 3, we have seen this is a total, and m dot 8 which is extracted, right, and this we can call it basically the fraction of steam extracted, that is y, and rest of the things will be 1 minus y, this will be also again y. So, if you look at how much fraction, I mean percentage wise you can say, or fraction we can say, this y being taken over here, and the rest of the things is being extracted is y 1 minus y of the total whatever m dot 3 is there, like total mass flow rate. So, that will be helpful for us to analyze and then look at it. So, then I can write down S 3 is equal to y H 8 plus 1 minus y H 2, right. And that is basically, if you look at that is the thing which will be, it will be entering, and then H 8 is coming. So, that you will get a higher H 3. Otherwise, it could have been suppose y is equal to 0, what will happen? S 3 will be same as that of the S 2, and which is a very small, like then it will be even y is equal to 0, there will be no extraction, right. Y is equal to 0 means there is no extraction, no regeneration, right, of the heat. So, at the state 3, so if you look at there, the steam must be saturated liquid, and if you mix together in an open feed water heater, then naturally it will go to the saturated state. But if you go for a closed feed water heater, you need to ensure it. So, therefore, that is also quite complex. Suppose instead of here, and if it is not coming here, it will become here. If you go for a closed feed water heater, then it will be problematic. Again, you will have to compress it, and two phase flow is difficult to compress. So, therefore, open feed water is advantageous than that of the closed feed water heater, right. But however, people do use both. So, hence equation use 1 basically used to determine the Y, that is the extraction steam extraction fraction, to have a saturated steam at 3. And if you look at heat added in the boiler, what it is? Basically S7 this point and H4 here, and rest of the heat is coming from the your what you call the from the water feed water heater, right. So, the heat rejected is how much? That is H9 minus H1 into 1 minus Y, that is heat rejected. And if you look at, if the Y could have been 0, then what could have been? This could have been a larger. That means, we are gaining some heat being from the rejected heat and adding to the system, adding to the your cycle, right. So, the thermal efficiency basically will be equal to W net divided by Q in, and the if you look at the work done in this basically can be put in a little different way. That means, the heat in minus heat out, and if you look at what is this? This is basically Q in, right. This is Q in, and what is Q out? Q out is basically 1 minus Y H9 minus H1. This is basically Q out, and divided by S7 minus H4, that is the of course, the Q in. This is Q in. So, you can find out thermal efficiency very easily, right. And the work done is basically S7 minus H8 plus 1 minus Y H8 minus H9. If you look at the work done will be reduced definitely, because you are taking some what you call steam out of it, and if the fraction is very small, then it will not really affect much, but however, there will be reduction in the net work extracted by the turbine. And of course, the pump also you need to have more extra work as compared to the simple cycle, and H4 minus S3 we are giving there some amount of work, otherwise you could have given from here to there, right. This is the extra work what you are giving, and of course, 1 minus Y S2 minus H1, right. This is being little bit reduced, this is also additional work. So, that net work output also will be reduced to some extent. So, the optimum therefore, it is very important to optimize it, otherwise you will trying to do enhance the thermal efficiency, it may happen you may land in giving like decreasing it, or may not be enhancing further like. So, one has to optimize the number of stages of reheat and regeneration. Generally, regeneration is not being used alone, it is being clubbed with the reheat. In other words, the combination of the reheating and the regenerative system is being implemented in actual steam power plants, right. So, and also optimization is very important, and these are the basic equations which we will be using by for optimization of the steam power plant, which is a very interesting and very important subject, particularly those people who will be getting into the mechanical engineering and other things, they will learn how to optimize and what are the things. Again, you will have to do some exergy analysis also, like exergy means availability, and do a lot of optimization, basically reducing the irreversibility in the system, and also adopting the innovative ideas of how to basically the maximize the work output with the least heat input. So, that is the thing what you need to look at it. So, what we will do? We will now take an example and try to see some of the points what we discuss, right. And this example is related to a regenerative system, and which is added to a 5 megawatt steam power plant, and it operates on a simple Rankine cycle, right, rather simple Rankine ideal cycle I can say, and steam enters into the inlet of turbine at 5 megapascals, right. This is 5 megapascal and 673 Kelvin. So, what is this point? If you look at this point is basically S7, that is the pressure. Pressure here is what you call 5 megapascal and the temperature is T7 is 673 Kelvin and gets expanded to condenser pressure, that is your condenser, this is your condenser. So, that is your basically 5 kPa. Keep in mind this is 5 megapascals, right. If you look at 0.1 megapascal is equal to 1 atmosphere, right. So, it is 50 atmosphere pressure. So, and this is a kPa, very low pressure, generally low pressure being maintained at the this thing at the condenser. A suitable amount of steam is withdrawn from the turbine at 3 megapascal. So, this is the place which is steam is extracted and this is 3 megapascal. This pressure if you consider that this is, because this is a basically constant pressure line, you remember that this is a kind of thing. So, and remaining what you call steam is expanded in the condenser. So, this is expanded in the condenser pressure level, that is 5 kilopascal. Then the pressure of the steam is raised to 3 megapascal to get mixed with the extracted tip from the turbine in open feed water heater, what we have just now discussed, right. And we will have to determine the quality of the steam at the exit of turbine basically here and net work output per unit mass and then thermal efficiency, that we will have to what you call do. Now, if you look at how to go about it. So, if you look at what we need to find, we will have to find basically x9, right, and you will have to find out net work output per unit mass and we will have to find out the thermal efficiency. So, how to go about this? How to go about? Basically, what you will have to do, we will have to, we know this point, right, because from the superheated steam table, right, I can get this from superheated steam table at 5 megapascal and 673 Kelvin. I will get the properties. What I will get? I can get H7, that is 3195.64 kilojoule per kg, and similarly I can get the entropy. Do I need entropy or not? 6.6458 kilojoule per kg Kelvin, right. That means this point I know. And of course, you may say that why I need it, because I will have to find out this point, I will have to find out x9 also, right, and I will have to find out how much work is being done in this expansion from 7 to 8, right, that I will have to find it out, and I will have to find out also how much steam is extracted from the turbine, right. And so, for that I need to know this state, right. That means I will have to know this, what is the quality of here, quality at station 8 and also the 9, I need to know that, and once I want to know the quality, how I will get it, because it is not given in the problem. So, how I will get it? I will have to use the isentropic expansion condition, that is what? that is S7 is equal to S9 is equal to S8, S7 is equal to S8 is equal to S9, that is the isentropic expansion, right. So, therefore, I can use that and find out the quality and then look at it, and then once I know the quality, I can evaluate the properties here, because I know the saturated condition from the steam table I can get corresponding to 3 megapascal this point, and I can get also this point. So, if I know quality, I can find out what will be here. Similarly, 5 megapascal I can get this point here from the saturated steam table, and also I will get saturated vapor conditions here, and then if I know, I can evaluate very easily H9, and then we can do the calculation, right. So, let us look at that. From saturated steam table at 5 kilopascal, I will get this data. This data is basically V1 is equal to Vf, that is this condition, right, is equal to 1.005 into 10 power t minus 3 meter cube per kg. This is basically specific volume. Similarly, H1 is equal to Hf is equal to 137.79 kilojoule per kg, right. And I can get HFG, because HFG is required, right, that is the heat of vaporization. HFG is 2423.66 kilojoule kg, and I need also entropy, right. Entropy will be S1 is equal to SF. Is it required, this one? 4763 kilojoule per kg Kelvin, and S that is your SG is equal to 8.395 kilojoule per kg. That you can observe one thing, that at a what you call SF liquid entropy is lower as compared to the gas entropy, right, or the vapor entropy. Now, okay, and similarly we can get also the other data, right, from the what you call the corresponding to 3 megapascal, right. So, let me just write down at 3 megapascals, right, at 3 megapascals from the saturated steam table, I can get these values, that is basically Vf is equal to S3 is equal to 1.115 into 10 power 3 minus 3 meter cube per kg, and Hf is equal to H 3 is 721.1 kilojoule per kg, and I can get Hfg is 2048.04 kilojoule per kg, and I get Sg is equal to 6.6627 kilojoule per kg Kelvin. So, if you look at, we have got all the data points, right. Is it something missing? If it is missing, you can get from the saturated steam table or the superheated steam table, right. Now, we need to find out the what you call X8. So, we know that what will be the S8, S8 will be equal to S7, right, and this is known, this S7 is known or not, S7 is known. How? From the superheated steam table corresponding to the 5 megapascal and 673 Kelvin, we have already got it. So, that is equal to X8 SF plus 1 minus X8 what you call SG, yes or no, right. And from this I can get X8 is equal to S8 minus SF divided by the SG minus SF. I know these values, S8 I know, SG I also know. So, if I substitute these values, I will get 0.996. It is almost equal to the 1, you can assume, but of course, it is not exactly 1. Okay? You can approximately say it is equal to 1. That means, it is on the saturated vapor line itself, closer to that. And by knowing this X8, I can find out what H8 very easily. What is that? That is basically X8, right, or I can put in a little different form, that is HF plus X8 HFG, right. So, HF, this point we know, right, saturated. So, this is known and this is X is known. So, therefore, I can substitute these values. Let me put this number 71.1 plus 0.996 into 2048.04. Okay. I mean, it is equal to 2760.9 kilojoule per kg. So, in the similar way, I can find out X9, right, because we know that S7 is equal to S8 is equal to S9. So, from that similar way, I can find out X9 is equal to S9 minus SF, right, SG minus SF, and this SG and SF corresponding to what? Corresponding to this pressure. What is this pressure? What is that pressure? That is basically 5 kilopascal. Corresponding to that you will have to put, and when you put that thing, you will get 0.78. Okay. Are you getting? So, similarly, you can find out H9, we can evaluate H9 as H9 is equal to HF plus X9 HFG, and we know these values. So, you will get basically 2028.25 kilojoule per kg. But by knowing this, is it possible we can find out net work done? Is it possible? We cannot. Why? Because if you look at W net, right, will be what? Will be Q in minus Q out is equal to S7 minus H4, right, minus 1 minus Y H9 minus H1. I can do this way, or I can do like what is the net work done S7, I can put this how much work done between the state 7 and 8, and then I will do also what is the work done in the between state 8 and 9. then I will have to find out compressor work and minus it, I can do that way. This is one way. There is another way also you can do, right. I can do this way, basically W turbine minus W pump. That means, in this case 2 pump are there. So, we will have to add, this is equal to basically W P plus W 2 P, right. This will be the W. Similarly, in turbine, high pressure turbine and low pressure, then you will have to do all those things and do that, right. But this will be little simpler way. So, we know the S7, right. Do we know the H4? Do we know H4? We really, do we know or not? Right. So, we need to find out what is that, and then we do not know this Y, right. We know this H9, already we have evaluated H9, we know this H1, H1 is saturated condition. So, therefore, we know. So, this is known, we need to evaluate Y, and we will have to evaluate also the 4 H4, right, and then we can do that. What is Y then? Y, if you look at, is basically H3 minus H2 divided by H8 minus H2. Am I right? Am I right? So, that S3 is known to us or not? So, S3 and S2 is known to us. So, we need to find out this S2, right. How will find out S2? S2 I can find out is equal to V1 into delta P, yes or no? V1 is known, delta P is known. So, that delta P is what? Delta P is, this is 8 megapascal, right, and minus this 5 kilopascal will give me that, and this is, if you look at S2 is basically 137.79 and I am sorry, this is plus H1 it will be, right, because H1 is known, this is also known. So, this is kilojoule per kg, right. So, H8 is known to us, and S3 also known to us, right, because that will be a saturated condition with that. So, if you get the S3 is equal to 721.1 kilojoule per kg, and this is known, and all these are known. So, you will find out this is basically 0.22. So, if I know this thing, right, and similarly you can find out H4 you can find out minus H4 minus H3, right, is equal to V into delta P, in this case 8 megapascal to the what you call 50 megapascal, right, and then you can, this is known to you, like, because this is corresponding to saturated condition. So, you can get that as basically maybe 752 kilojoule per 7 to 7 kilojoule per kg kind of things. So, once you know this thing, right, I can find out the net work S7, right, and H4 minus 1 minus Y H9 minus H1. So, all are known. So, you will get basically something 999.98 kilojoule per kg. So, once you get, then you can get the thermal efficiency is equal to W net minus Q in minus Q in is equal to W net minus S 7 minus H 4. So, this is S 7 H 4, both are known. So, you will get basically this will be not right, this will be H 3, okay, plus S 3, that will give you that. So, if you substitute these values, because this is known, this is known. So, you will find out that this will be something 0.4041 is something 40.41 percentage, right. So, by this way you can solve these problems, right, and look at it, and one can see that, compare with that, and then you will find out in this case if you take the same problem without regenerative, the thermal efficiency will be coming something 38.4 percentage. So, that means this is without regeneration, right. So, therefore, there is an increase in the thermal efficiency, but it need not to be always true, that depends upon the how you have designed and how it is being operated. So, what we will do, we will be basically looking at is there any other way of increasing the thermal efficiency by lowering the condenser pressure, right. And if you look at that, I can lower the condenser pressure, but there is some limitation, as I told, that less than the 7 kilopascal people is not really interested to do that because of some problem. So, if it is lower, this is earlier it is operated 1, 2, 3, 4, right, but now the pressure is being lowered, that P 4 dash is less than the P 4. So, therefore, like there is a more work done here, if you look at this is your area which is having what you call work done. But however, like there is a penalty one has to pay, because here one has to add some certain amount of heat kind of thing. So, if you look at the net increase in work output is basically area 1 what you call 4 dash and 1, this portion, if you look at this portion is the net work net increase in work output, right, this portion. But however, this portion like that is what you call x dash 1 dash 2 dash and 2 of course 1 x, this portion if you look at this portion is basically increase in heat input one has to give, right. Of course, this is the more additional heat, and then one can also enhance the thermal efficiency. And we will stop over here, and we will look at in the next class basically about how to incorporate the losses into the system and analyze it for the Rankine power.